Welcome, welcome to the pre-recording of the second part of lecture 18, scheduled for the beginning of week 7 of our 8-week summer course. In the first part, we defined polynomial time reduction on how we can reformulate problems in polynomial time. And we say that they are polynomial time reducible if you have an efficient algorithm. For the second problem, you reduce it to, then you also have an efficient algorithm for the first problem. So in this second half of lecture 18, we will consider another problem that reduces to the independent set problem that we discussed in the previous part. Okay, what is the satisfiability problem? We consider Boolean expressions. So Boolean expressions are expressions that are essentially computations with bits 0 and 1, false or true. So 0 has the interpretation false, 1 is true. What are the elementary operations? We can negate a value. We can add values modulo 2 then. So we can place the or to the values, or we can conjugate them, which corresponds to the multiplication. So multiplying 0 with 0 gives you 0, 1 with 0 gives you 0, etc. One has these truth tables which are realized by basic logic gates. So then we can define what is a clause. A clause is a set of terms where all the terms are conjugated. There is the or operation between all terms in the clause. So the terms in the clause are either the variables or they are the negated values. So one can make a drawing, a picture of such clauses as logic circuits, which are composed by the logic gates using the not operator or the or operator. Okay, with clauses we can ask if they can ever be true, for which inputs do we obtain 1 as output. So you could see these clauses as expressions similar to arithmetic expressions. So we compute with these zeros and ones, modulo 2. If we assign values 0 or 1 to the variables, and then when we evaluate the expression, do we obtain 1? So the question is there an assignment of the variables for which the clause is true? Okay, we say that the assignment satisfies the clause if that expression, the clause then evaluates to 0, if you follow all the rules of the Boolean logic. Okay, so time for a more general formulation. So if we have a collection of clauses, then we can ask whether there is an assignment of the variables that makes all of them true. So here is this formally defined. So if you have an assignment that makes all of these clauses true, then we say that the collection of clauses is satisfiable. Now, again, so if we have n variables, all possible choices of assignments leads to 2 to the power n. So obviously this problem is well defined because we do have a way of checking just by trying all possible combinations, but that leads to 2 to the power n steps. Obviously, not a polynomial time algorithm. We will see that if we have an efficient algorithm for the independent set problem, then we can actually solve also the satisfiability problem. That will actually be the main topic of this lecture. So time for an example. So here we have three clauses for three Boolean variables. So the first clause is x1 order or not x2. And we conjugate this with not x1 or not x2 or x2 not x3. So if we assign all the variables to 1, then this evaluates to 0. So that's not a satisfying assignment. If we, on the other hand, make all the variables 0, then this results in a satisfying assignment. So therefore, for this set of clauses, there exists a truth assignment that yields true. So when we say then that the set of clauses is satisfiable. Okay, so we can reduce the satisfiability problem. Let me first state the satisfiability problem, or SAT for short, as given by a collection of variables which take the values 0 or 1. So that's what it means to be a Boolean variable. And then a set of clauses. So these are expressions in these variables which use the or and also the negation operation. So if we then consider the conjunction of all these clauses, can we find an assignment of these variables that computes to 1? In another way, is there ever an input for which the entire expression is true? It turns out that solving this problem is equally difficult as the tree set problem. The tree set problem considers a number of clauses where every clause has exactly 3 terms. Okay, and that seems kind of strange, and that is kind of an interesting property. So I mentioned the combinatorial solution where we consider all possibilities, and that leads to 2 to the power n. So in some sense, intuitively, that would be also the way how to go for these exactly 3 terms. All right, let us now show a polynomial time reduction from the simpler problem, so the problem where we have conjunctions of 3 set clauses that have exactly 3 terms in them, to the independent set problem. So we had the independent set problem in the first part of the lecture, or in the previous pre-recording. We ask for a subset so that any 2 elements in the subsets are not connected by an edge. So then the question of the independent subset problem is that if you have a graph and a number, is there an independent set of at least that size equal to the given number k? Okay, we will show that if we have an input of the tree satisfiability problem, that can be translated into a graph, and that asking whether the conjunction of clauses is satisfiable is equivalent to asking whether there is a solution of the independent set problem. So what this means is that if we have a black box that solves the independent set problem, then actually we can solve the tree satisfiability problem. So the independent set problem might be an easier problem to solve. So can we reduce in polynomial time the tree satisfiability problem to the independent set problem? We will do this by example, so there is an algorithm for this. So here we have an example of the tree satisfiability problem. And you can see that for the graph, every clause consists of a triangle, and the vertices are labeled by the nodes that are the variables in the clause. So the nodes appear with their negation, so the x bar is not bar. And then you have to draw an edge between x and x bar, because it means that if you select 1 for x, then you have automatically the value for x bar. So in this graph, we have the triangles. So x, y, z are the three variables in this conjunction. Obviously, in a conjunction, you never write twice the same variable. So that's why we connect these three in the same clause, and we have a link, an edge, whether when between the variable and its negated one. Okay, so we have defined therefore the graph with as many vertices as we have terms, and actually have many total terms and in the entire set of clauses. So we have 3 clauses, 3 variables in every clause, so 9 vertices. And then we connect all the nodes in one clause, and then we make also connection between the nodes and their negated ones. Okay, so the title is Satisfying Clauses and Independent Sets. Notice that independent sets means that you select those vertices that are not connected by an edge. So here is the solution for this problem. So we select the green, so we take in this solution. So if we select x, y bar and z bar, then we solve the problem. So how do you solve this problem actually logically? This every clause is a statement of ors. It suffices that one of them is true. So you need to have one green, so x is 1 here. Now if you select x equals 1, then x bar, not x, you can't select. Then, but if you select y bar, then that makes that second clause true. And then you have one possible other choice, z bar equals 1. So the green selection corresponds to an assignment, a truth assignment, which makes this expression, this entire expression, evaluate to 1. And it also corresponds to the definition of an independent set. So we can verify that for these 3 green nodes, there is no edge between them. So if this graph has an independent set by selecting one element of each, you can satisfy the collection of clauses, 1 and 1 and 1 is 1. And that illustrates by example why the two problems are equivalent. Okay, formally, if you have now a general collection of clauses, then every clause corresponds to a triangle in your graph. The vertices in the graph are the vertices. So now I should say that the vertices in the previous graph, it may have confused you. I had vertices with the same name, x. Now here, all the variables, all the terms in this clause corresponds to unique vertices in the graph. So if we have k terms in our graph, then we have 3k vertices. So we have a triangle. We have 3 terms in every clause. So we have 3 edges. So, and again, what I pointed out, if the clause is true, it suffices that one of them is true. So, and now we connect the clauses, looking at vertices that correspond to their negations. So that actually implies if you have in a pair of clauses, we add the edge between the nodes that corresponds to the terms where the variables are negated. So the recipe is given here. So what is defined here mathematically corresponds to an algorithm. So we have a recipe to connect the 3k vertices in this graph. We have rules. Okay, so look at another example. Consider here a Boolean expression of 3 variables. Again, it's a slight variation of the example. Define the corresponding graph. And also, do you see the connection between a satisfying truth assignment and an independent set? Or it could be that for this problem, there is no satisfying truth assignment. You can also ask again, is the solution to this problem unique? That's another problem. That's another valid question. So the purpose of this numerical exercise is that if you can solve this exercise, then you understand the previous slide. Okay, now we have that the satisfiability, the tree satisfiability, is equivalent to the independent set. So if we have a solution to the tree satisfiability problem, then actually we have an independent set. So, and the k here corresponds to the number of clauses. The k corresponds to the number of vertices for which there are no edges between them. So this, again, it's important to notice that what it means to be having an independent set of size at least k. So we will show that if the one problem is satisfiable, then we can actually compute, we can show that we do have a set, an independent set of size k. Okay, so how do we do this? So what it means in the graph is that every clause corresponds to a triangle, and we conjugate all these clauses. So then every node, every triangle in this graph must have at least one node that has value 1. Okay, so if we collect all those nodes, so these were the green nodes in our examples, then we have an independent set. Okay, so we will show this if you have by contradiction. So suppose that if for any pair there would be an edge, so that would mean that we wouldn't have an independent set, but that would contradict the satisfiability, because what we have a connection between the nodes of different triangles if they are different, if they are negated. So if we have a 1 in one clause, then the corresponding connected term should have the value 0. So it can't, but we selected only those vertices from every triangle for which we had a 1. So that means that there can't be any uh, edge between two valuable vertices that we picked. Okay, so from the solution of the tree satisfiability problem, we do have computed an independent set. Does the opposite happen? Well, if we have an independent set of size k, then we can actually compute an assignment. So how come? Well, if we derive the truth assignment, so we have k variables, so we actually set the assignment depending on whether the node appears, the vertex appears in that independent set or not. So we have assigned the values according to a recipe. So we have actually found a truth assignment. So all the variables are actually defined. And by the way the graph is constructed, we have at most every vertex, and because the size is k, we assigned 1 to every clause. So, and that satisfies the clause. Okay, we had a theorem that tree satisfiability is polynomial time reducible to independent set. Well, we have the construction of the graph. So we have 3k vertices. So we run linearly through all the clauses, and every term in the clause corresponds to a vertex. We also construct the edges. So while we are adding the vertices for every clause, we add 3 edges, and then we scan again, adding the edges when there are negations. So there is a polynomial time algorithm to construct the graph. Then we call the black box solver. The black box solver for the independent set solves the problem. And then from the answer of the independent set, we can actually construct, and it's good that the proof of the lemma is still here. So we have an algorithm for constructing the truth assignment, because if there is an independent set of size k, then we will assign a 1 to every clause, and we will actually have the satisfiability. And it is an if and only if statement. If we don't have a size k set, then we will have too few ones in the clauses. And we will conjugate or multiply it with at least one zero, and that will render the entire expression zero. Okay, I hope that this was sufficiently clear that we can actually solve the satisfiability of a logical expression by a graph problem, by deciding more geometrically on the independent set of vertices in a graph. Okay, so one last discussion on how the problems relate. So we have the property that if one problem reduces to another, and that other problem reduces in polynomial time to yet another, then the first problem also reduces in polynomial time to yet that other problem. So here we have z reduces in polynomial time to y reduces in polynomial time to x, then z reduces in polynomial time to x. So adding up a number of polynomial steps is again a polynomial steps. Also, the number of polynomial steps to the black box solver adds again up to the same polynomial step of polynomial times. So the composition of polynomial time is again a polynomial time. Okay, why is this relevant? Because we have already showed that the vertex set cover reduces to set cover. That's a more general problem, so that was in the first set. Independent set reduces to vertex cover. So actually now the more general problem, the tree set cover problem, you can reduce the tree satisfiability problem by this transitivity theorem to the set cover problem. So if we do have an implementation to solve the set cover problem, then we can reformulate it. We can use that to solve any tree satisfiability problem. Okay, so one last exercise. So we said that the independent set problem was actually more generalized by the set packing problem. So exercise 3 asks you to generalize, to describe the relationship between the independent set and the set packing problem. So if you solve that exercise, and actually the point here is that you can show that by the transitivity problem, if you solved exercise 3, then actually that solves also the reduction of the polynomial time reduction of the tree satisfiability problem to the set packing problem. So the main justification here is the solution of exercise 3 and the transitivity problem. So in some sense that exercise can be solved quickly, but you have to use an example where you construct explicitly the connection between the two. Okay, so this was lecture 18, scheduled for the start of the 7th week in our 8-week summer course, in which we defined and applied the notion of polynomial time reducibility, here in particular to the evaluation of logical or Boolean expressions.